Finding the x-intercepts, in other words the roots of a function, is not always easy. Well, with simple functions, such as polynomials, they can be found by factoring. With more complicated functions, they're difficult to find exactly. For this reason, we'll often need to approximate the x-intercepts of a function when they can't be found exactly. As we saw with linear approximation, the tangent line to a function is oftentimes a good approximation to the function itself. Thus, we'll approximate the x-intercept of a function using the x-intercept of the tangent line. For example, if we have a function whose graph looks like this, suppose we want to find this x-intercept. Well, the idea is we can't find it exactly, so what we do is we find a point close to it, and we take a tangent line at that point. And we will get an intersection point here, which will be a fairly good approximation for that x-intercept. So, we're going to need a formula for this intersection point, for the x-intercept of the tangent line. It's going to be given by this formula here. The x-intercept, x0, is going to be the point A we're taking the tangent line at, minus f of a over f prime of a. Great, so let's keep this formula in mind and see how we can use it to approximate the x-intercept of a function. One of the problems with the approach I've mentioned so far is that when using linear approximations, we always want to make sure to take the tangent line at a point A which is close to the point we're interested in, right? If we don't have x and a close together, the linear approximation won't be a very good approximation. So if we're trying to approximate the x-intercept of a function with an x-intercept of a tangent line, we'd really like to take the tangent line at a point which is close to the x-intercept we're looking for. However, it turns out that the most easy way to find a point which is close to an x-intercept is to actually use another tangent line, a tangent line which is farther away. So, if we're trying to approximate an x-intercept, we're going to use what's called an iterative method. We're going to repeat a procedure over and over again. We're going to start from some random point x1, which may or may not be close to an x-intercept. We then draw a tangent line at x1. We find the x-intercept with that tangent line. That's going to be a place which is closer to the x-intercept of the function. We're going to find a tangent line then at that point x1 we just found. And we're going to use that tangent line to find a point x2, which is going to be closer to the x-intercept. Then we're going to use x2 to get an even better approximation, x3. We're basically going to be repeating this procedure over and over again, and as we're doing it, we're going to be using this formula, xn plus 1, which is basically the next approximation is the previous approximation, minus f of xn over f prime of xn. We're going to keep repeating this procedure, getting better and better and better approximations until we've got one that's good enough for us. So let's see what this procedure looks like. We want to find the third approximation, x3, to the x-intercept of the equation f of x equals cos x minus x, and we're going to start from x1 equals 1. So the first thing we need to do is we need to find the formula we're going to use to get x2 from x1 and x3 from x2. To do that, we first need to take the derivative. F prime of x is going to be negative sine x minus 1. So this means that our formula is going to be xn plus 1 is going to equal xn minus, right, f of xn over f prime of xn, which means it's going to be xn minus f of xn is going to be cos xn minus xn. F prime of xn is going to be negative sine xn minus 1. So this is the formula we're going to be using each time to find the next approximation from the previous approximation. So we're going to do it with x2. x2 is going to be x1 minus cosine x1 minus x1 over negative sine x1 minus 1. So let's plug our x1, which is 1, into this formula and see what we get. We get 1 minus cos 1 minus 1 over negative sine 1 minus 1. This gives you a number that's approximately 0.75036. It's got more decimal places. I'm going to cut them off just to save space on the page. Okay, we've got our x2. It's going to be a sort of better approximation to the x-intercept of this function. So now we want to find x3. x3 is going to be x2 minus cos x2 minus x2 over negative sine x2 minus 1. And basically we're going to put in the 0.75036 in here. Minus cos 0.75036 minus 1 over negative sine 0.75036 minus 1. And what does this give us? This gives us approximately 0.73911. So the third approximation, x3, is this number, 0.73911. It's a fairly good approximation to the x-intercept of this function. This method, Newton's method, can be used not only to find x-intercepts of functions, but also to find roots, solutions of equations. Basically, if you want to find the approximation to the root of the equation, x cubed plus x equals 1, we just mentioned that the root of this equation, the solution of this equation, is the same as the x-intercept of the function f of x equals x cubed plus x minus 1. Basically, those are the same things, so we're going to use Newton's method. We're going to find the x-intercept of this, and that'll also be the solution to this equation. Okay, so let's take our derivative. F prime of x is going to be 3x squared plus 1. So my formula is going to be xn plus 1 equals xn minus f of xn, which is xn cubed, plus xn minus 1 over f prime of xn, which is 3xn squared plus 1. Great. So we can use our x1 to find our x2. x2 is going to be x1 minus x1 cubed plus x1 minus 1 over 3x1 squared plus 1, plugging in 0.5 for x1. What we're going to get is 0.71429 as our approximation. Then if we want to find x3, we're going to take x2 minus x2 cubed plus x2 minus 1 over 3 times x2 squared plus 1. So we're basically going to take the 0.71429, plug it in here. We're going to get a number which is approximately 0.68318. So this is our x3. It's the third approximation to the solution to that equation. Oftentimes you want an approximation which is correct to a given number of decimal places. For example, we want to approximate an x-intercept to 6 decimal places of precision, or 10 decimal places, or 3 decimal places. In general, we can't always know the error in our approximation without knowing the exact value of the x-intercept we're approximating. Basically, we can't know how far we're off by without knowing the exact value of what we're looking for. However, there's a guideline which will be useful in any iterative method of approximation which involves finding better and better approximations. The guideline says that if two successive approximations, if two approximations in a row, share the first 10 decimal places, so they're the same in the first 10 decimal places, then these first 10 decimal places are correct. For example, if we got our x4 to be 0.93345 and x5 to be 0.93336, these two approximations agree on the first 3 decimal places. Since they agree, those decimal places will likely not change in the future, so we can say they're correct. The x-intercept to 3 decimal places is going to be 0.933. So let's use this idea to approximate the positive root of the equation x squared equals 10, correct, to 3 decimal places. So the first thing to mention here is I haven't told you what x1 is. So basically we want to pick an x1 that's close to a solution of this. Well, x squared equals 10, well, it's close to the equation x squared equals 9. 3 is a solution to that. So let's pick x1 equals 3 to start off with. Then, of course, we need our formula. So the first thing to mention is that the x-intercept of the function f of x equals x squared minus 10. The derivative here is 2x. So my formula is going to be xn plus 1 equals xn minus f of x, which is x squared minus 10, over f prime of x, which is 2x. So we'll 2xn and xn. Again, remembering it's f of xn and f prime of xn when using this formula. So then we're going to start with x1. x2 is going to be x1 minus x1 squared minus 10 over 2 times x1. We plug in 3 to that. What we're going to get is an answer that's approximately 3.1666666, etc. Okay, that's the first approximation. Then we can use that approximation to find x3. x2 minus x2 squared minus 10 over 2x2. Now, approximately, if you plug this in, we get 3.16228. Okay, these two agree on the first 2 decimal places, but not on the third one yet, so we're going to keep going. x4 is going to be x3 minus x3 squared minus 10 over 2 times x3. This is going to be approximately 3.162277. Okay, these two agree on the first three decimal places, so those first three decimal places will probably be correct. So, correct to 3 decimal places. The solution is 3.162. There we go. It's an approximation to the solution of x squared equals 10.